Okay, now it's the time to learn what the work is. Despite of its general meaning in everyday conversation, in physics work has a very specific definition. Before I start, I should remind you the concept of components of a force. Consider a force like F making an angle of theta with the horizontal, and I'm gonna find the component of that force on horizontal axis. Let's shine a downward vertical light on that arrow. If it's really a physical object, it will make a shadow on horizontal axis this big. So it's gonna be the component of force on horizontal axis. It's Fx, okay? In this right triangle, I can define the cosine of theta as the adjacent divided by the hypotenuse. So cosine of theta seems to be Fx divided by F. If I rearrange this equation, Fx seems to be F cosine of theta. F cosine of theta is the effective part of that force on horizontal axis. Means that if you apply a force like 10 Newton and if it makes an angle of 60 degrees with the horizontal, basically the Fx is gonna be 10 times cosine of 60. Cosine of 60 is a half, so the answer is 5 Newton. Means that although you apply a force of 10, but on horizontal axis, it has just an effective component of 5 Newton, not 10. Now let's define work. Here I have a force of F acting on an object, and that force is making an angle of theta with the horizontal. So the component of that force on horizontal axis is going to be F cosine of theta, and let's suppose that the object has a displacement of x. Work is defined as multiplication of effective force and displacement. So effective force times displacement is work. In SI unit, work is measured in joules, force is measured in Newton, and x is measured in meters. We can have an alternative perspective. Instead of having effective force on the direction of the displacement, I can make it like that. I can find the effective displacement on direction of force. How? Here I make a component of x. I find the component of x on the direction of force. So it's a right triangle, and again, as usual, I will find the component of x on the direction of f as x cosine of theta. Let's say x cosine of theta is the effective displacement, okay, at the direction of force. So here again I can define the work as the force multiplied by effective displacement. Again, work is measured in joules, force in Newton, and effective displacement in meters. Both of them are accepted, it's up to you. In general, W is gonna be Fx cosine of theta. Okay, now let's define 1 joule. 1 joule is the energy required or work done when a force of 1 Newton acts through a distance of 1 meter. Here I have W equals F cosine of theta times x. Let's say F cosine of theta, the effective force is 1 Newton. X is also 1 meter, so it's gonna be 1 joule. That's all. This is how can we define 1 joule. Okay, let's answer this question. The thrust, the driving force of a microlight aircraft engine is 3.5 10 to 3 Newton. Calculate the work done by the thrust when the aircraft travels a distance of 15 kilometers. Okay, it's very easy. Let's say the direction the thrust force is acting on the airplane is horizontal and the displacement also is horizontal, same direction. So here F cosine of theta actually is exactly 3.5 10 to 3. Let's plug in the values, and here 15 kilometers is converted to a meter, so we need a 10 to 3. That's all. The answer seems to be 53 megajoules. Mega here stands for 10 to 6. A large box is pulled a distance of 8.5 meter along a rough horizontal surface by a force of 55 Newton that acts at 50 degrees to the horizontal. I calculate the work done by the force. Here you see the force is 55, but the effective force is not going to be 55. We should find the horizontal component anyway. It makes an angle of 50 degrees and to the horizontal, and the displacement is 8.5. Let's find it. First of all, the horizontal component, the effective force, 55 times cosine of 50. So F cosine of theta times x. Again, I plug in the values and the answer is 301 joules. A cart rolls down a ramp that makes an angle of 25 degrees with the horizontal. As you see, the horizontal force of magnitude 6 Newton acts on the cart. It's the horizontal force. The cart moves a distance of 0.75 meter down the ramp. So the distance traveled is 0.75 meter. Calculate the work done by the horizontal force. By definition, work is Fx cosine of theta. Let's say this is x. I know the x, I know the force, but I don't know the angle. Let's find it. Let's say the angle is beta. You know that if I draw a line parallel to the ramp and then a couple of horizontal lines, here it's 25. It must be 25, okay, accordingly. And here I have a beta here. Let's say this is alpha. Alpha and beta are supplementary angles. They add up to 180. So beta is going to be 155 degrees. So here beta is 155 degrees. Or here, theta. So let's plug in the values. 6 times the displacement and cosine of 155. The answer is negative 4.1 joule. There is a very interesting feature. When the cosine of theta is negative, the work done also is negative. So for obtuse angles, when the force and the displacement make an obtuse angle, the work done is negative. The woman in figure walks along with a constant velocity holding a suitcase. How much work is done by the force holding the case? Here, as you see, the direction of motion is horizontal and the force is vertical. So they make an angle of 90 degrees. Cosine of 90 is 0. So the answer is 0. Keep in mind, when the force is perpendicular to the direction of motion, there is no work done. Okay, let's make a general result. Here, there is a force like F and there is a displacement like X. I make an angle of theta. If theta is an acute angle, something between 0 and less than 90, the work done is positive. When theta is 90 degrees, means the force and the displacement are perpendicular, W is 0. And when theta is obtuse, larger than 90 degrees, of course less than 180, we expect negative work done. Work done by a resistive force. Suppose that there is a force acting on the object like F, making an angle of theta with the horizontal, and the effective force is F cosine of theta, okay? Actually here the resistive force is against the running force, the forward force. So they fight. Let's say the value of the resistive force is 80 and the other one, the running force, is 100. So the net force is 20 to the right. Means that the object will accelerate rightward. Anyway, let's suppose a displacement of 20 and find the work done by each force. First, the work done by the running force, by the forward force. Here I have the work done by F as F cosine of theta times X. F cosine of theta is given as 100 and X is 20. So the answer is 2000 joules. The other is the work done by the resistive force. It's going to be F cosine of 180 because the resistive force makes an angle of 180 degrees to the displacement. So it's going to be negative 1 and X again 20 meters. So the answer is negative 1600 joules. The work done by the net force is going to be the subtraction of, actually the addition of these two, but necessarily we are subtracting them. 2000 minus 1600. So the answer is 400 joules. The work done by the net force can be obtained using a different approach, easier approach. How? Let's say the net force is F, or let's say F net. F net seems to be 100 minus 80, so let's say F net is 20. And then the displacement is 20 meters. Okay, so the work done by the net force is gonna be F net 20 times 20. So it's again 400 joules. It's easier. Okay. A car moves at a constant speed of 54 km per hour on a horizontal road. The work done by the driving force of the car in 1 minute is this, 180 kilojoules, okay? Calculate the distance traveled by the car in 1 minute. Let's do it in SI units. The distance traveled is very easy because it's in a constant speed, so we can easily use the formula of x equals vt. But v must be in SI units. Okay, v is 54 kilometer per hour, and I divided by 3.6 to convert it to meter per second. It's gonna be 15 meter per second. That's all. And the time is 1 minute, actually 60 seconds. So let's plug in the values. And the answer is 900 meters. This is the part A. Part B. The magnitude of the resistive force acting on the car. Magnitude of the resistive force is very interesting. Basically, the car in general is acted by two forces. One of them is the forward force of the car, the other is the resistive force, okay? The car is moving at a constant speed. There is no acceleration. According to the Newton's first law, it's in equilibrium. So what the forward force is, the resistive force is the same. If I find the forward force, the magnitude of the resistive force is the same. So if you are going to find the resistive force, you can easily find the forward force. It's the same. Let's do it. The work done by the forward force is Fx. Suppose that the forward force is totally effective force. Oh, there is no need for cosine of theta. Cosine of theta actually is cosine of 0, and it's 1. Now, let's plug in the values. 180 kilojoules, kilo is 10 to 3, force is my goal, and 900 meters, the displacement we already found. So it's 200. If the forward force is 200, the resistive force also is 200. That's all. It's very easy. So they are equal and opposite. Part C. The work done by the resistive force. Work done by the resistive force. Guys, be very careful. I have a displacement of 900 meters, x, a forward force of 200, and also a resistive force of 200 to the left. Okay, why? Because as I mentioned, the car is moving at constant speed. Okay, here there is a very easy approach. If the work done by this force is 180 kilojoules, the work done by the resistive force is the same but negative. That's all. Why? Because the work done by the resistive force is resistive force times cosine of 180 times the displacement. Everything is the same except cosine of 180, so it's negative 180 kilojoules. That's all. Now look at a very interesting example. Let's say there is a force acting on the object, 20 Newton, and it has a displacement of 6 meters, okay? Let's draw a force x graph, force distance graph, okay? The force is 20, so it's gonna be a horizontal line for 6 meters. If I'm gonna find the work done, seems to be Fx, because cosine of theta is 1, theta is 0. So F is 20, X is 6. The answer is 120 joules. Now let's find the area under this graph. It's the same. Very interesting. 20 times 6. Same value. So the work done by the force can be the area under the Fx graph. Can I generalize this approach for any other type of graph? Of course you can. Even if the force is not demonstrating the same behavior like a horizontal line, you may be curvilinear, you can use the same area under the graph. If you can find it, it's gonna be the work done. The graph shows the variation with displacement d of a force F that's applied to a toy car. Okay, the force is not a constant force, it decreases, and the total displacement seems to be 4. Calculate the work done by F in moving the toy through a distance of 4 meters. It's very easy. You know, actually when I use F is equal to Fx cosine of theta, whatever, we have already supposed that F is constant. For the case that F is changing as a variable value, normally you cannot use this formula easily. You should use integration. Actually, the work done is integral of F times dx. Instead of the complexity of dealing with the complexity of this integration, I can use the area under the graph. This is why we use that. It's very easy, geometrical solution. So the area under the graph is the work done, and here I have an area of a triangle. Vertical side is 20, horizontal side is 4, divided by 2, the answer is 40 joules. An initially stationary ice hockey puck is hit by a stick. Okay, the graph shows how the force exerted by the stick on the puck varies with the distance traveled by the puck. You see the force has a very complicated behavior. It raises to a maximum, then drops to zero. Okay, determine the peak force F max on the puck. Okay, it's very good. The work done is given to be 30 joules. The work done means the area under the graph, so I know the area under the graph. Here, the area is 30 joules. The horizontal side is 5, but times 10 to negative 2. You see it's 10 to negative 2 banked here. And the vertical side is my goal. Okay, the area of a triangle is the vertical height times the base divided by 2. And here the answer must be 30 joules. It's very easy. Actually, F max seems to be 2 times 30 divided by 5 times 10 to negative 2. That's all. It's 60 divided by 5, which is 12. So it's 12 times 10 to 2. The answer is going to be 1200 Newton. This is the value of the peak force. Thank you for watching this video. See you soon.